Welcome everyone! I'm your instructor Sean. It's great to see you back. I'm totally excited about this lesson on how to build a Raspberry Pi robot step by step. In this lesson, we'll use analog sensors and the ultrasonic sensor to create an autonomous robot. It's going to be tons of fun. We're going to dive right into analog to digital conversion, the IR distance measuring sensor, line sensor, and the ultrasonic sensor. All the code and schematics are found in the description below. If you have any questions, please leave a comment. Let's get started. In order to interface an analog sensor to the Raspberry Pi, we need to use an analog to digital converter, since the Pi does not have an ADC. The sensor will output a varying voltage, which will be an input to the analog to digital converter. The analog to digital converter is connected to the Pi using a serial peripheral interface, or SPI. So the analog voltage will be converted to a digital representation that the computer can process. The ADC that will be interfacing to the Pi is the Microchip MCP3008 10-bit 8-channel ADC. In our first experiment with object detection, we're going to use the infrared sensor. The way it works is the IR LED will emit an infrared beam, and there will be a reflection back to the detector. The angle is then determined, and the distance will then be calculated. This sharp IR sensor has a range of 4 to 30 centimeters. The part numbers are listed in the description below. The IR distance measuring sensor is mounted on the Rover 5 chassis that we used in lesson 3 of this series. Here's the full schematic of the Rover with the IR distance measuring sensor. As for the motor control, I'm using the Cytron MDD10A motor driver board. And now we're adding the sharp IR sensor, which is connected to the analog to digital converter. The ADC communicates to the Pi via SPI. Note that the VRF and VDD 3.3 volt reference. When performing a test of the output voltage from the sensor, you can see the voltage increases as the object becomes closer. The voltage decreases as the object moves further away. First, we're going to test our infrared sensor by using the analog to digital converter. If you like to use the text editor, simply type nano and a file name. I'll call it analogtest.py. We're importing a couple libraries here, one of them being the spidev. Also time. These couple lines are setting up the communication. You may see that I have a getValue function. This is the function that reads the analog to digital converter, the MCP3008 that we have connected. Within these brackets will be the channel that you have the sensor connected to. An important thing I wanted to teach you is how to properly reference code. If you're using code from another source, make sure you use this format: the title, the author, date, code version, and availability. I found this code on the Linux and User and Developer magazine. If you were to find this online, please include the web link. In the main code here, under while true, this is continuously repeating. We're going to print the raw value from the A to D. That's the value from 0 to 1023. And we'll have a delay of 300 milliseconds in between each reading. To run the script using the command line, simply type python analogtest.py. Since the ADC has a 10-bit resolution, there are 1024 quantization levels. Therefore, you will see the numbers 0 to 1023. As you move closer to an object, you will see a higher digital number. As the object moves away, the number decreases. This flowchart will describe the algorithm for the autonomous movement of the rover. It will first start going forward. It will determine if there is an object or wall that's detected. If no, then it will continue to go forward. If yes, then the program will create a random number, 0 or 1. If it's 0, then it will go backwards for 1 second, then turn left for 2 seconds, and then continue to go forward. If no, in other words, if the number is 1, then it will go backward for 1 second, and then turn right for 2 seconds, and then continue to go forward, and the loop repeats. Since I'm writing more complex code, I prefer to use a compiler with debugging tools, such as Thonny, as opposed to using a text editor. Also note, in this environment, I'm using Python 3. Take a closer look at the code in irrover.py. Here we import our libraries, rpy, spidev, time, and the new one here is random. This library will generate the random numbers that we talked about. Okay, we're going to set mode. We have the SPI communication open. LED to pin 21. I have an LED that's on to indicate that the system is powered. Now please review lesson 3 to look at the motor control code for the Rover 5 and the Cytron motor driver board. Here we have a pin that goes for direction and pulse width modulation. Direction is for forward and reverse. Pulse width modulation is for the speed control. So we set up those PWM ports. We have the function for the get value from the A to D that we looked at just recently. And we have functions to control the rover for right, left, forward, backward, and stopping. Now under while true, the code of the flowchart is shown here. First is going to go forward, then is going to check the data from the IR sensor. If the value is greater than 200, then it detects a wall or an object. It will then create a random number, an integer, 0 or 1. If it's 0, it will go backwards for 1 second, then turn left for 2 seconds. Then it will go back up to forward. If that random number happened to be a 1 instead of a 0, it will go backwards for a second and turn right for 2 seconds, then go back up forward, continuing repeatedly. Let's take a look at how this works. Alright, the way the line sensor works is the LED will emit an infrared signal. If there is a white surface, then you will have a reflection that's received by the photodiode. It will measure the intensity of the beam that's being reflected. If there is a black line, then a less intense beam is returned. And that's how it can determine the difference between the two different colors. Next up, we're going to look at this analog line sensor. This schematic is the test circuit for the analog line sensor. For the code, we're using the same analog test.py that we used earlier to test the infrared distance measuring sensor. In this line sensor breakout board, we have 3 outputs: the analog out, ground, and the VCC 5 volts. The ADC has a 3.3 volt reference and VDD. As you can see from this test, when the analog line sensor is above the black line, there's a higher number value. When it's on the white, then it's a lower number. The ultrasonic sensor is a popular device for distance measuring. The way it works, it will send out a sound signal, and the sound signal will be reflected back to the receiver. It transmits a pulse of 10 microseconds, 8 cycles of ultrasonic bursts. The time it takes for the reflected signal to return to the detector is determined, and then the distance is calculated. To calculate the distance, we use the formula distance is equal to the speed of sound times the time. So that will be 2 times the distance, which is there and back, speed times the time. The speed of sound is equal to 343 meters per second. Therefore, distance is equal to 171.5 meters per second times the time. We will express this in centimeters per second, which will be in the calculation in the Python code. The way this is connected is we'll have VCC to 5 volts. Trigger will be an output from the Pi. In this case, will be connected to GPIO pin 20. The echo is an output from the sensor, which is an input to the Pi. And recall that we have to have 3.3 volts going to the Pi. So we're going to use a voltage divider. And the echo will be going to GPIO 16. The values we're going to use is 1K and 2K. The voltage divider is calculated like this. We want to know what the potential is of R2. So VR2 is equal to R2 over R1 plus R2 multiplied by Vn. This is the voltage divider calculation. So 2K over 1K plus 2K multiplied by 5 volts. So VR2 is equal to 3.3 volts. Also, don't forget that ground pin. Here's the schematic to test the ultrasonic sensor. Note the voltage divider circuit that provides a 3.3 volt input to the GPIO pin. In ultrasonic.py, I have pin 20 on the Raspberry Pi connected to the trigger, pin 16 on the Pi connected to echo. You can see that trigger is an output and echo is an input. It sends out that 10 microsecond pulse, waits back for the echo, determines the difference in time, then calculates the distance. I currently have the ultrasonic sensor positioned toward the wall. Let's hit run to see what the distance is. It is currently 10.52 centimeters. That's awesome! You can use the ultrasonic sensor as an alternative to the IR sensor. The advantage of this device is that it has a longer range that it can do distance measuring as compared to the IR sensors.
Cool.
Today, you learned how to use the infrared distance measuring sensor, the line sensor, and ultrasonic sensor. How will you use this in your project? I look forward to seeing your creations.